So let's start. So thank you very much for coming. So we are now open. So this special lectures by the winners of World Cultural Council Award 2019. I am Hideo Kigoshi, Vice President for Research, and on behalf of the University of Tsukuba, I would like to welcome you all. Now, let me introduce the first speaker to you. Dr. Wang is chair and regent professor of Georgia Institute of Technology, USA, and also the director of Beijing Institute of Nano Energy and Nanosystems. He is a physicist, material scientist, and engineer specialized in nanotechnology and energy science. He is known as a father of nanogenerators, which he has developed for self-powered systems and large-scale blue energy. His pioneer's work is expected to change the world in the near future. He has published over 1,500 peer-reviewed papers and has an enormous impact on the nanotechnology community. The title of his lecture is Nanogenerator for Self-Powered Systems, Internet of Things, and Large-Scale Blue Energy. So please join me to welcome Dr. Wang to the stage.
Good morning, ladies and gentlemen. It's my honor and a privilege to stand here to give a technical talk on our advances in those fields. I want to use next 40 minutes to review the solutions we potentially find that face our world in the near future. As you see from this image, the world is fast changing. Our environment, our climate, especially the energy we use. As you see from this video, you can see in the last 40 years, the world North Pole, the ice melting largely increased. So which is due to the global warming. So we use fossil energy for decades. How long can we sustain? How long we can go? Is there any new energy possibly subsidize or support us for the future? So my talk is our near future thought on how to solve the world energy over the large scale or even on a smaller scale. As you can see, this time evolve here. You can see the area of ice drops dramatically. Okay, so this is our huge worry for the humankind. So when you look at the energy in the human history, it plays a vital role, especially from the railroad power to the telephone, to the space technology, automobile, and even to the modern electronics. Our energy has been largely dependent on coals, oils, but as we advance into smaller things, nanotechnology, Internet of Things, artificial intelligence, and what are the energy we possibly could use? Do this energy have the same characteristic as before? The answer may not be. Let me show you what's the difference. Our current technology for power delivery is such: use power plant, use cables, or use energy storage unit. Do this solve all of the problem or not? Okay, the answer, we do not solve all the problem. So what we are facing now, we face the distributed electronics, mobile electronics, just like each of us have a cell phone. In the future, we're gonna have more and more. So these have vastly distributed mobile and most cases wireless. How do you power them? So by 2025, 30 billion objects will be moving. So this is another energy we are facing. For the last 2 decades, I've been working on this problem to find potential solutions, okay? So they say, why do we need those so many electronics? Because these days, we need to monitor everything. You know, they know where you are, where you have been located, the speed at which you move, all the things, so big data. So this is the era of Internet of Things, sensor network, big data. So we enter a new era, the era of Internet of Things, big data, and the sensor network. Okay, so this is the near future we are facing. We want to do everything for that. So look at that. How do we solve this problem? Traditionally, we have a power plant, have the cable deliver power to fix the sites, to Tsukuba University, to this conference center, fix the sites, cable, solve it. But now, when you move this wireless, concentrate energy, go fixed site, go distributed energy, order the energy delivery to disordered, wired to wireless. So we are facing a diversity of energy application. So you can see this is just irreversible. So I call this the entropy application in energy distribution. So this is why you view it. It's just like an entropy. That's the world goes. The second law of thermodynamics. That's what tells us irreversible. Okay. What's the entropy? Just use a simple example because people are work on the physical chemistry. They know what the thermodynamics is and what entropy is. Entropy is a simple idea, but fundamentally important. It's from concentrated to distributed, ordered to disordered. You can see this is a drop of ink put in water. After 10 minutes, it's dispersed in water. Nothing changing in total energy, but irreversible. That's called entropy. That's what the distributed electronics bring us to. So this is what the face. So how to solve the problem? Cisco company did a survey. And they found if we rely on a battery, because we can solve a lot of problems, but for moving object, a large percentage of internet thing would be impossible if you just use battery. Because battery cannot self-charge. A person has to charge a battery. Just like your cell phone, every evening you have to plug in. The battery will not walk off the plug and say, okay, I need to charge. So therefore, that's the limitation. So therefore, we need to build a solar power system, and this is the area I have been working for the last 2 decades. So first one, we show this one. I proposed the idea 2005, and I wrote this article, say, solar power nanotechnology. That time was a dream. So can you make the device so small, tiny, can we be self-powered, can detect the signal, process signal, and a transmission to the external side of the body? Is this possible? So that was called self-powered system. So now let's look at what the possible solution for this, okay? Let me cut off this thing here, okay? Then, how do we view this one? From ordered energy to ordered applications, from ordered energy to distributed application through batteries. But this cannot solve all the problem, so we need to harvest energy from our environment. Body motion energy, mechanical energy, heat, solar, wind, whatever we have to solve our energy need. So therefore, we need both. We need both right now. Okay. So what are the possible solutions? And we published a paper in 2006. This was a paper. That time, we was trying to use nanomaterials to convert little tiny mechanical energy to electric power. But the power was so small and almost useless that time. It was just a scientific concept. But we proposed the idea, so-called nanogenerator, for the first time, and solar power system. Following this dream, I have been chasing for the last 15 years to develop this system and hopefully provide new solutions, fundamentally important solution for that. I'll give you some story behind that. So this was the original idea for that. And I wrote very clearly solar power. By that time, I did not know we would be solve this problem or not, but it was a dream list, okay? So what was the solution? That time used piezoelectric effect. For people who learn materials, they know piezoelectricity is due to non-central symmetric of a crystal structure. On the mechanical strain, cations and polarize give you a dipole moment. As a result, you're going to see this potential can drive the electron to flow in external load back and forth. So there was a simple idea, use a piezoelectric effect. A lot of Japanese group work on this as well, on piezoelectric for energy generation. So we demonstrated, for example, use a single nanowires. We can use let's say, finger motion. You see, this is finger motion. Okay, finger motion. You can generate AC power as a here. Okay, that's the all demonstrated. Use heart beating. The first heart beating driven nanogenerator possibly for soul powered pacemaker. This was more than 10 years ago. So where did our story start? Our story was here. 2005, when I finished the paper, I had a lunch with the students. I said, guys, you never forget about this day, and I think we face something exciting. If you ask me that time, I said, why do you feel something exciting? I don't know the reason. I just felt as though this something could be important. We finished the paper that day. You can see this December 25th, 2005, the Christmas day. So I had a lunch with the students. Said, okay, guys, we finished. Let's submit it for publication and see what happened. That was this time. After more than 15 years, we particularly increased the power output, and we coined a number of new fields. So if you don't chase the dream, you will not have the dream. If you don't chase the dream, you will not realize the dream. So therefore, I'm very grateful for this one. So I told these guys here, and today I'm mainly focused on most recent events. How do we do it? How do we do it? Just give you a story, and from this point, so the dream change. 2011, when we do the piezoelectric factors, okay, if you go back, you see this? When we do the piezoelectric, particularly enhanced performance, we accidentally found a triboelectric nanogenerator. Let's do the mistake. First was a mistake, and I thought it was a mistake. Must be some artifact. So we went double check, triple check, do multiple percent proof. Yeah, it was triboelectric effect. Then I go detail here, and tell you the story behind that. Ever since then, the whole world responds enormous for this one. Let me come to the story about this one. Okay. So what is triboelectric? Let me show what we found. Okay. How do we solve the problem? This is the classical way we do power generation, and this is the way we do called triboelectric nanogenerator, TENG. See the way it works? You can see this one have run at a fast pace. If you have a high frequency, the voltage barely drive a couple of lights. But this at a low frequency can lit up many lights simultaneously. So the key difference is at the frequency dependent. Our TENG is a linearly frequency dependent. Electromagnetic generator is a quadratic. So at a low frequency here is cut off. So therefore, electromagnetic cannot be useful for low frequency, like a body motion or light wind. The wind has to be higher than 5 meters per second, otherwise you cannot generate power. So therefore, ours particularly low frequency. Let me tell you the detail here. You said, what's new here? After we discovered this one, 2011, we demonstrated very many things. Nanogenerator could be a micro-nano energy source for small electronics, for power shoes, even for environmental cleaning. And also, then have solar power system. We have so many sensors, shape adaptable, transparent, MEMS, all can utilize this as a sensors because you convert mechanical triggering into an electric signal. That's a sensor. Okay. Lastly, can we contribute to the large energy need we are facing? So I propose the idea. We are still chasing this dream right now. Okay. So how good we can do? From our study, ever since it was first invented here, we already improved the power output to 500 watts per meter square. The conversion efficiency is 50% or higher. So the performance is dramatic. Then when I present this one, you think, well, what is the fundamental science here? Let me tell you the science side about this one. You can then say, we come back to technology. So here's the outline on my technical talk. First one, what does the physics become behind quantum electrification? We think we know this for 2,600 years. But the physical interpretation is not well established. The second one, the principle of TENG, figure of merits, application, and future perspective. So when you talk about triboelectricity, everybody knows. We experience it every day, every moment. When you slide your shoes on the floor, triboelectricity occurs. How do we explain that? When we teach a student for electricity, they say, oh, we use a plastic rod, rub an animal fur, we get an electrostatic charge. But the question was, why the plastic rod has to be negative charge, the fur has to be positive charge? We did not have a good interpretation. we took as the facts. So that's the fundamental question we did not answer. So when you look at this one, it's like a blind man in the literature touch an elephant. Depends which angle you look at that. And different people have different opinion. Also complicated, solid with solid, liquid with liquid, gas with liquid, all occurs. And also some people say electron transfer, ion transfer, material species. Which one? So let me just give you a brief interpretation, then we go back to technology application and broader impact. When you look at the textbook for middle school kids that teach electricity, the first one is electrostatic charge. They cannot explain why side is negative charge here or positive charge here. Why? Then they talk about the second class is electric current. Let's talk about electron flow. How come from an electrostatic charge become a current flow? This question was not well explained in a middle school textbook. Just say, okay, here's current, you go. The light flashes, that's all. So let me answer one by one. So first one is physics contact electrification or triboelectrification. So when we do our TENG, we do this, two plastic materials, physical contact, triboelectricity occurs. Then you measure the current. When you live up here, we used to say capacity change give you the current. You can see the current. As you see in this video, you tap in here, you're going to see the current flow like that. You can see the current flow like that, okay? Which you see the flash like that. So once we put this in the furnace, I had a curious question, it was 3 years ago, said, let's put in the furnace, see how long can it sustain, okay? So we put in a furnace, heat up. We find by 583 Kelvin, there's no more output. That means the triboelectricity disappears. And we can start a decay rate in room temperature at 443 Kelvin, at 583. So we have the systematic data. We can simulate data. We find this thermiotic emission is responsible for this one. It's electron transfer. We have a lot more data. Furthermore, say this is heat generated. How about the photon excitation? So we place this triboelectricity on the surfaces and then use the light to illuminate. We find the charge pertain on the surfaces depends the wavelength of the light. You can see this is 300 nanometer light, no heat effect, very little heat effect. And this is 280 nanometer, but 240 you have a sharp turn. There's a critical number there, critical energy, because the energy depends the emission of the power here. Okay, so that's the energy related to this photon electron emission. So we did the second one. I said, let's do this one. We have a dielectric surface, we have metal tip, contact. We can deliver charge on the surfaces. Let's change a bias. We can switch from negative charge to positive charge delivered respectively on the surfaces, on the surface for that. Okay, so this again shows is electron transfer. If you have ion transfer, you cannot switch the sign of an ion by change the bias. So therefore, we did a number of manipulations and I show this the fact. So I will skim the interpretation a little bit because it's more technical here, just show you. The second question we try to figure out is that if you do two object contact, how close they have to be? How close they have to be for charge transfer here? We found if you have two atoms here, this is the equilibrium position here, this is the interatomic interaction potential. But when you squeeze one against the other one, so the distance between two is shorter, maximum electron wave function overlap or electron cloud overlap. In this region, triboelectricity occurs. Electron exchange occurs. Exchange occurs. And this is because in this one, it has a potential barrier between the two drops. So I draw a schematic to show you how the potential barrier drops as you squeeze one against the other one. Just like, triboelectricity means we call squeezing, okay? Why do the squeezing? It's because one atom close the other one, so the electron transfer occurs. So I draw a schematic here. This is one atom between A materials, another atom between B materials, and if they're separate a little too far, the barrier is too high, no electron transfer. But when you push one close to the other one, the barrier drops. You say, why the barrier drops? So this comes from, I teach the students the electron sample interaction class. Say, okay, when you have one atom and two atoms, you push one against the other one, the potential well is this. So there's no barrier. So the electron can jump to here and release the energy. Then electron transfer occurs. Okay? Then the electron remain here because will not jump back because no way to provide this energy to come back. So therefore, after you separate the two, negative charge, positive charge. Use this model, we explain a lot of phenomena we know in our daily life for the triboelectricity occurs. I will just try to make things simple, okay? Then if you heat up, of course, thermiotic emission, electrons gone. So this is the first question. How did the triboelectricity occurs? We have a lot more recently on a liquid and solid, many cases. I'll skip that. The second one, if you have, let's see, electrostatic charge, why do they have to flow? Okay? Second question. Let me ask the second question. We are familiar with this one. This is the traditional way to do power generation. Faraday invented in 1831. Used magnetic flux, magnetic field, Lorentz force driven electron flow in the metal rod have current. Ours different. Our difference goes to Maxwell's time. When Maxwell proposed these four famous equations here, and he introduced displacement current in order to make all these four self-consistent and satisfied continuation of current or conservation of charges. He theoretically proposed that. But he died at a young age, 49. And until 1886, 7 years after he died, electromagnetic wave was observed. Okay? So it was just mathematical at that time. But he said, displacement current is not an electric current of moving charge, but a time-varying electric field plus a contribution from slight motion of charges bounded in the atom. So he wrote this is displacement current. So now this is a medium polarization, but the one term was missed there was the surface charge. If you have other field, look, for example, strain field induced surface polarization was not included in that equation. So if you have piezoelectric effect, triboelectric effect, we should introduce here. So let me see, how do we introduce that in a simple way? So we try to modify Maxwell's equation to derive the power output we observe. How do we do that? Let's look at this term specifically. Let's do a simple case here. Piezoelectric case, piezoelectricity on the mechanical strain, polar charge generated. You have electron flow from one end to the other through the external load. That's you see the power here, okay? So how do we see that? The way this medium polarization is given by this equation. This is a polarization, electric field. This is a displacement vector. If you substitute here, you get here. Permittivity by electric field. So displacement current is permittivity, the derivative of electric field. You can find if E is 0, this is 0. If no electric field, there's no displacement current. That was supposed to be. Use this one, he derived the Maxwell, the electrical magnetic field. We use it every day, now every moment. All your wireless communication depends on this. Now, if you have a surface polarization charge, this is the electric field induced, and this is a non-electric field induced polarization. So I introduced this equation in 2016. Okay, after we introduced this one, we immediately derived all the equations we needed to explain this phenomenon. So therefore, we expand Maxwell's displacement current to include surface charge contributed polarization, and of course, all our theory following that be following. This sounds like too theoretical for this group. I just explained to you the schematic for that. What we changed? We changed the Maxwell equations to have this term included, which was not included in that one. So when I met my advisor, Professor Archie Hoy at the Cavendish, and he asked me, so you add this term in, how many chapters should be added in Jackson's textbook on electrodynamics? So I said, well, at least should be one more chapter. Just a joke, okay? So this was the theoretical part. Fundamentally, what's the difference? You say, well, you do some innovation. Where are the innovations? Derivative of magnetic field give the displacement, the electromagnetic generator. The medium polarization give you the nanogenerator here. Then we have piezoelectric effect induced and a triboelectric effect induced. Inside here runs the displacement current. This was first proposed by Maxwell. We always observe the conduction current. Where the two meet electrode form a loop. That's what we see. So it used to be, we don't know much about this one. We just say, okay, we see conduction current. We just say conduction current. Then you say, well, if this is fundamentally different from classical, what are the impact? What are the broad impact? Let's see that. The impact is this one, is electromagnetic generator depends on electromagnetic induction, resistor-free electron flow by Lorentz force. Here is electrification, counter-electrification, and electrostatic induction. It's called capacitive current. You're going to see this have the advantage of high current, low voltage, high efficiency, high frequency. So that's why you have to run faster, okay? This one is high voltage, low current, high efficiency, and low frequency. That's what we human motion related. In our artificial intelligent time, robotic time is human related, low frequency. That's the key difference here. And so we have key advantage here. So what's the basic contribution? You can see when Maxwell proposed the Maxwell equation, he introduced the displacement current, from which he derived the existence of electromagnetic wave, which proves experimental first time 1886. As today, all this dominate our life every day. But back to then, 1870s, 80s was just theory. Okay, now if we add a term due to non-electric field, we produce the theory of nanogenerator for energy, for smaller scale energy, for sensor network, Internet of Things, low frequency energy harvesting, which is this part. So even this is small. We hopefully next few years, 10 years, will grow up. Will grow up. So this opens door for people work on the materials. We have a lot of materials. People work here. What are the materials? For example, if you look at the displacement current, what are the best surface area we look at? What are the best material have triboelectricity? What's the best material have permittivity? What's the best have robustness? All materials issue. We open a new venue for people working in chemistry, materials, and even in mechanics. So after you've done this one, how do you calibrate this one? So-called figure of merits. So for people in this audience, they work on energy, either work on solar energy, thermoelectric energy, or heat energy. They have their own factors to standardize this one. 5 years ago, I asked my group members, what is our factor? How do we calibrate this one? After a few years' work, we finally derived the factor. We can calibrate performance of our technology in order to compare with others. So we inspired by the Carnot's machine. And without going through the detail, how do we work on it mathematically? We work on the voltage, charge curve, calculate area. What's the maximum area we got? That's the total energy we output. We derive some equations. To skip that, I'll just show you the results. We have two results. The first one, for the materials, the best surface charge density is the standard of merit, a figure of merit, like a ZT factor for thermoelectric materials, okay? Then we have a structure figure of merits because you have a sliding mode, a contact mode. We have another one. This one free online, you can calculate what you got. If you look at literature, you think this is well established, like a materials, another genome. It is not well established in literature. Let me show you. If you look at the textbook, they say, okay, here we go. Triboelectric series. This is better than the other one. It's more positive here, it's negative. There's no number associated with that. No number associated. Until a few years ago, I said, we must have a number to quantify that. So we have to be invented a new measurement technology to measure this quantitatively, to standardize the equipment for measurement, standardize the materials for measurement. After 3 years' work, we have a table which have a specific number for calibrate this one. So the world will have a reference for that. So if I talk so much, you think, well, this sounds like too theoretical. This is too fundamental. What's the broad impact? Let me show the broad impact, okay? 4 major areas: micro nano power source, solar power sensors, blue energy, and high energy. Let me show you the fun part. You're going to see videos from here. If you make this one, triboelectric nanogenerator in a shoe insole here, you have add no weight, very little, tiny, soft, and you're going to walk, freely walking. A person freely walking, the light flashes. Put in your shoes. Low cost. You can use any material you want, okay? Any material. If you use silicon, you can make this shape adaptable, twistable. It's a sensor and also a little power generator. Or put in an arm, shape adaptable, flexible. You can tap in different positions and light flash. You can see those ones you can apply to robotics, anything you want to. Because material is broad. You can choose pretty much anything you want. How much power you can generate? If you put it on the floor 1.5 feet, it's a board, like a half a centimeter thick. You put it on the floor, a person freely walk. A cup of water came out. It's not huge, but sufficient for many things we are care about that, for the area we are interested in. So this just show you we can be able to make this low cost, put on the floor is a power generator, and no other technique you can do that, okay? For medical purpose, implantable medical devices. We use the breathing of a little rat to drive a simulated pacemaker. Today, we'll be able to, the animal breathe once, the power generator be enough to jump the pacemaker 3 times. This is a decade of work. You can see that. We recently applied this for large animals. We test on a 50 kilogram peak for solar power pacemakers. You see the output of this one even reaches like 60 volts and a microampere current. This is enough for drive the pacemaker. So that's why the community is so interested in an implantable medical device for brain stimulation, for nervous stimulation, for drug delivery internal body, even for drug delivery externally. This have brought. A lot of people talk about fabric. We wear fabric every day. They want to make a smart fabric. How come a fabric be smart? Let me show you a way. You can see we can sew this one in different ways, like company here. This one use the contact electricity between different fibers. It's become a power generator. You put this one, power generator here. There's 4 effects to make a fabric to be functional. Number 1, capacity effect. Second one, piezo-resistant effect. Both need the power. If you have no power, it does not work. The third one is piezoelectric effect. The last one, triboelectric effect. But piezoelectric effect is specific materials. Not all the material have it. Triboelectric is diverse, universal. You can choose this one. You can see this one. And then you put them into matrix here. So you can see here, somebody touch here, you know that. That's why you put on this floor. Somebody walk over it, you know it. But the self-generated signal here. You can even make a motor. This model, electrostatic model driven by TENG. Let me show you without going through it. Let me show this one. This is a model, electrostatic model here. See, this is the TENG. You slide once, you can see this is run at 1,300 round per minute. So for medical application, just use body motion, you can drive a motor inside at a high pace. So this shows the solar power system again. The second part I like to talk is solar power system. Solar power. We have a system. How do we make them solar power? We make a board like that. We can type in different parts. You see, when you type in different parts, the power is being delivered. Okay? And it's second typing here. No amplification, whatever. Right? No amplification here. If you cut the power line, no problem. It's just self-generated here. The output is sufficient for you to do a lot of things. Each of us use computer every day. We can make a computer keyboard to record the way you're typing, the force you're striking, the distance between the, you can see this one. This the keyboard we made here. Let me show this video. Students here, I'll show you that. All right, keyboard. And we made this one underneath the keyboard. And striking the key, he's striking the key, all this electric signal generated because we represent the force, space between typing, everything here. Utilize which we can identify who typed it at an accuracy almost 99%. So not only just like a voice recognition, this is your typing behavior recognition for that. Medical, can you make super sensitive sensors to measure the shape of the heart beating, heart pulse, and also from which you can derive the blood pressure. So we are developing this one. I think this is very useful because can instantaneously measure a person's blood pressure conveniently. So we try to do this one, you can see, for medical purposes. Robotics. Can you make a robot hands smart? So grab a cup of water is different from grab a piece of iron. because the force and the sense is different. This is the smart hands towards robotics, okay? So we made robotic make here. If you use this one, two pieces of paper, punch holes one on the other one. When a solid wave triggered, it generates signal. It can be a hearing aid. Can you believe a hearing aid without amplification? Directly, a solid wave trigger, a few volts come here. Let me show this bit, voice recorder. So the first one, show you this one. This is music. This is recording. The breadth of the frequency we can tune by the shape design here. Okay, you can use this one. This is a paper-based. Let me cut this off. They cannot stop. I want to show you the robotic communication. Non-stopping is there. Self-generated, I'm sorry about that. Self-powered. This is the communication robot. Okay. The machine, I don't know who talked. See, they didn't recognize. The second person. Okay. The machine recognized who said. Just use our paper-based TENG as a microphone. And also it can be a recorder. Okay, let me see. Yeah, last one. This is the recorded and playback. And we keep 90% of the accuracy of sound by this simple paper-based microphone here. So we have a video show you. Next one is, I work with my colleague at Georgia Tech. They work on this one. You can see.
What objects and surfaces
You can see it.
We
Used paper-based microphone for wireless
easily be embedded
microphone.
on everyday objects to enable them with self-powered sound sensing and sound energy harvesting capabilities. Saturn consists of materials which are thin, flexible, and cheap. Paper and a dielectric called PTFE. The paper has a series of holes laser cut in a specific pattern. Both layers, PTFE and paper, are coated with a thin conductive layer of copper and joined together using glue dots in a grid-like pattern.
Use the contact separation
When
electrification.
sound reaches Saturn embedded into an object or surface, its structure microvibrates, resulting in both layers getting in contact, generating negative charges on PTFE and positive charges on the copper-coated paper. As the layers separate, potential differences build over the two copper layers, causing the current to flow.
They just
towards
explain the simple mechanism how it
vibration
work
results
in a
layers
video.
getting closer and in contact again, resulting in a reverse direction of current flow
Yeah.
that completes the cycle of
That's the
electric
sound signal
communication.
came out.
The structure, material design, and method of embedding Saturn on objects has been optimized to maximize the recovery of sound and the power harvested from this electrical signal. How can Saturn work in the real world? First, let's think about the modern home.
Alexa, play.
Right now, controlling smart home assistants can be tough. You must be in close proximity
For
the
smart
assistant
home.
to hear you.
Alexa, stop the music.
Saturn can solve this problem, as it can be easily embedded into everyday objects, like this nightstand.
Alexa, stop the music.
Allowing them to be ubiquitous microphones for interactions and control, extending Alexa's capability to hear from anywhere in the house. Let's look at another example in the home. Saturn can be used for providing in-room context. If we have multiple Saturn patches located on a table, it can help detect the location of people around it by the strength of the signal received.
Hi, how are you?
I'm good, thank you. How are you?
Like a so-called microphone.
Hi, how are you?
I'm good, thank you. How are you?
I'm good too.
Now let's explore how Saturn can be used in outdoor scenarios. In the presence of a loud sound, Saturn can harvest enough power to do small computing tasks like storing a bit in flash memory or to do transmitting wirelessly. Saturn-based sensors can monitor hearing safety in situations where sound levels exceed human tolerance thresholds, such as in construction zones, mines, music venues, airports, spaceports, and military environments. Similarly, they might be deployed to monitor sound produced by events like landslides, polar ice breaking, mine gas explosions, or military activity. Saturn can help indicate the area and direction of events. Saturn is a promising technology which opens avenues for battery-less remote
You can find this
sensing
video, I think, on YouTube. You can find it. Okay, just show you the one clip. Lastly, you say you can have a potential way for world energy. How? Okay. The world energy solver is a complicated problem, very difficult too. The nature gives us light, air, and gravitation. If you look at the ocean, the tremendous power, but to harvest such power extremely difficult because corrosion problem, growth of bacteria, everything on the surfaces make all this so inefficient and only works in shallow waters. If you deep waters, forget about that. That's just impractical. How do we do that? Let me find a way. Let me show you a way to do this, okay? First one, what's the advantage of our invention? So we built a disc-shaped TENG, an electromagnetic generator. Put on one axis. Let's rotate. Let's see the output. Use TENG to drive these three lights, electromagnetic to drive these three lights, and see which one comes first. Let me show you. These three lights, as soon as rotate, 80 rounds per minute, these three lights by TENG lit up immediately. But these three lights of electromagnetic still remains dark. The reason, because the output voltage is low. Theoretically, this is the reason. This is the reason. So the fundamental limitation. Until the rotation speed go up and up. Until when? Until about 350 rounds per minute, then start flash. This start flash. Okay, and then say, well, okay, so like here, higher frequency traditional technology works efficiently, but at low frequency it will not. So we are not trying to replace it. We do the things class technology cannot do. Then say, how do you solve this problem? Let me find a design. So we design a sphere. We put it in the water, and you can see this water, inside the water, the balls swing back and forth due to the wavy. Okay, so the balls sliding back and forth destroy the symmetry of the two surfaces, so the electron will flow back and forth here. So you see in the water here. Just simply like that. So this is the first step, single unit. How about multiple units? We can make multiple units as a networking. And each one can have substantial output. We can put it in shallow water, deep water, complicated situations here. All of them can work together. Regardless of good weather, bad weather, day or night, we hope this can be a sustainable, continuous power. In this case, in many cases here, it's more stable than solar energy because solar energy largely depends on weather. Okay, how do we improve? We improve a lot since we invented this idea a few years ago, okay? Instead of using a hard ball, we use a soft ball. You can see soft ball, we largely improve. You can see the soft content area become large. You can see one ball be lit up with that light. See that? In the water, just one ball. Okay? Recently, we amplify, because the wave coming, wave strike, and this in here. Another 10 seconds later, another one. So very low pace. So how do we amplify that? We use a pendulum idea. We can largely extend the working for many seconds after striking. So you can see this one. See? You can see this floating here back and forth. Right? All work together in here. And because amplified frequency here, we also can do that. You can see light wind. You can do light wind. If you have a heavy wind, normal traditional way works. But for light wind, even at home, at your neighborhood, in your front yard, it can work. But the traditional way cannot work for that. So this is the one. So therefore, what's the key difference? Class technology, magnetism, coils, the output power is the frequency of square. Then ours use polymer materials, organic materials, output is frequency, linear frequency. At low frequency, we have the killer application. So it's not a substitution, replace. It's do a class technology cannot do use. So we are talking complement, not replace one and the other one. So is this real? How far we go? Let me show you. We already tested water. You can see we put in this water, the floating, okay? And we already even study the hydrodynamics in water. We even, in a simulator here, this is the water simulator here, we already testing this one. So therefore, we have the hope can do this one. We have the confidence to do that in the near future. Recently, we already test out in ocean. Small setup, test the ocean. Okay, it's a baby step, but who do the first step? Okay, so after we've done that, so how much power you can generate? If we can optimize of this one, I theoretically calculate, utilize 400 kilometer by 400 kilometer area of surface area, 10 meter depth water, make it three-dimensional. The total power output is 16 terawatt. That's the total power consumption for the world today. Use three-dimensional design, not just a two-dimensional design. You can design in the water like that. So therefore, we have a dream we call blue energy dream. Blue energy dream. In the near future, we hope to realize for humankind to solve our energy need for that. You know, the beauty of this sphere is that it is fully packaged. Whatever grows on our side, whatever on our side, it doesn't matter. As long as there's no water infiltration. Or infiltration, okay? So I just got this video from a medium. It was made in Chinese, but you can see what they're talking about that, okay? This is what they talk about 70% of the surface area being covered by water. This is the classical way for energy harvesting. We use all right, they put on this, so it's a rotator here. You have to run this at a higher pace here, and you can get the power generation here. And so this is the way. Our way is this, put in the water like that, sealed, so no infiltration. Use polymer material field, floating. You can make it three-dimensional. You don't have it on the surfaces. You can some depth, water, okay? Then use the polar charge on the surfaces. If you're rolling back and forth, rolling back and forth. Simple design, okay? Simple design for that. Now we extend the lifetime a lot. We work on that, okay? So you can see materials choice, you can very diverse by that, okay? And then we can make it flexible for foldable electronics, use the TENG, and even can use the liquid and solid. So this one is completely sealed in the condition for that. And then we can, this is simulate for that, in the water for that. Don't put this on the way the ship goes. Don't put it in the way there's a vacation site. You can put the location that's hardly useless, hard to use at all. So we can design the patches here, okay? Patches here. Then you can design this one. So this is for the blue energy design here, okay? This animation is not quite right, but just the medium people draw that, okay? So you can see this in the water like that. Just an animation for that. We do experiment for that. Okay, as this, if you can make a patch like that, you can make a large patch, just like a solar cell. You can make a wafer like that. You can make many wafers, integrate that. Right? Okay, so I have a dream too. Integrate this with wind energy, with solar energy. We have a complete solution for the future too. Use whatever is available for the one. You can see this one. This is wearable electronics. We rely every day. Always worry about the battery. So future has no battery worry. Self-generate. Self-generate. Okay. So this is one. What are the commercial opportunity? Because like myself is a person on the science side, but we started commercial too. See how far we can go. If we never do it, how do we know we cannot do it? So we tried. We tried to look at, this is a survey by US company. They found distributed energy by 2021, in 2 years, will be $100 billion market, large business. So the first thing we did was pollution. You know, the car exhaustion pollution here. So how do we do that? I use this video. You can see this student blow through this one. The voltage generates a few hundred volts. We do the similar thing. When the exhaustion go through here, we have a voltage generator, do electrostatic absorption. Use this principle, we build the filter. We drive this car for 30,000 kilometers, still stand and perfectly stand, better than standard. for pollution treatment of automobile. For indoor, like indoor air filtering here. For offices, for cars, indoor air filtering is also marked. Build solar power shoes. So far, the first one is lighting shoes. The second one is foot health characteristic detection. The third one we can do, can we find a position? If you have old people that get lost, can we do the positioning? The small children that get lost, can we position for that? So this one do the shoes for that. And also the company like Samsung push very hard for wearable electronics. You have a lot of wearable things. How do we power them? Because the power is not that large, but if you can sustainably provide this one, that can continue to work. So as this field advances here, from very small, around the world, have 42 countries and regions, 420 units, 4,000 scientists work on an area. This was data a year and a half ago. So look forward. When something appears, looks, well, how far can this go? I believe that time, Faraday gave a public lecture. People don't believe that. Is this true or is something wrong? He gave public lecture education here. Years, centuries later, use this to manufacture things like that. So we never know how far we can go, but a scientific breakthrough will bring technology revolution, and also hopefully more than we thought today. A lot of things we cannot think about today, but once many people we involve electrical engineering, mechanical engineering, physics, chemistry, medical, environmental, whoever are interested, this one go here. So that's the end of my talk. Of course, 20 years work. Without just myself, I cannot do it. Many students work with me. I thank them for their contribution, postdoc, and also visiting scientists. So look forward. This is the roadmap. Roadmap. We're going to do 4 major directions. Micro nano power source. Even small power, but mobile, wireless, is satisfy the entropy distribution of power in our environment. Why do we weather get warmer and warmer? Because we burn everything, oil, coal, burn everything. Where the heat go? It's distributed environment, no doubt, right? So no way to recover. Then solar power sensors. This kind of immediate application. Anything motion, you're going to become electric. Then large blue energy dream. Those are going to take us time to realize. So I work not only in the fundamental science, but also work on the technology and also the broad impact to many areas. Hopefully one day we're going to impact the human life in some way. And so where are the future? As Lincoln said, the best way to predict the future is to create it. To create it. And use the imagination mind, and hopefully we can create something different or better than we are today. Hopefully find a solution for sustainable development of humankind. So let me go back to my slides. I'd like to thank the World Cultural Council. Council gave me this award. I heartily appreciate it. Thank you for your acknowledgement to my work. Hopefully our work will be useful for the world at large. Thank you.
Thank you, Dr. Wang, for your stimulating talk. So now, the floor is open for question and comment. So we have some time. Oh. Please, your name and affiliate.
So good morning. So my name is Dr. Takahiro Morio, University of Tsukuba. So I have 2 questions. So the first one is about this technology as a nanosensor. So especially outward use, there are a lot of white and random noise. And so in such condition, I'm wondering whether this sensor can happen something like quenching or adaptation. So does it happen? And the second question. So one of the problem of green energy is how to store.
Yeah, good question.
Yes.
Let me ask you one by one, okay?
Yes.
The first one is that the existing technology use piezoelectric factor, piezoresistant factor for sensors. like a piezoresistant factor, you have the supply of power. If you have no power, they cannot sense anything. Piezoelectricity give you a signal, okay? But if you want to build a piezoelectric sensors to a lot of substrate, it's very hard because they need some temperature to grow the materials, so specific material for that. Our effect is universal on any materials, any substrate, you can do this one. Number one. Number two, the output signal's magnitude. Just like I'm talking, you know, the paper vibration, the voltage generated 3 volts. A few meters away, wireless. You know amplification needed. So if you have a few volts output, the detection unit only need a millivolt sensitivity to detect it. But if you have a millivolts output, something that like we normally use like this one, you need a high filtering. Also, you need amplification, which need power, number one. Number two, the measurement equipment has to be sophisticated because you need a microvolt accuracy to measure millivolts signal. So ours is 1,000 times at least better, and it could be cheaper. So the first question. The second question is storage, right? Because like what do we use our cell phone, we need a storage. We do 3 things: energy conversion, nanogenerator, power management. Because when you walk, you can walk faster, slower. That's a random phase. Can we convert this random phase into ordered application? So we need a power management, the second one. The third one is energy storage. So we build a nanogenerator, power management, and a battery or capacitor, fully integrated, called self-charging power pack. This battery will not run out of power. As motion goes, it is self-charging. That's we do need a storage, but it's a different way of storage.
Yes, especially so, I think this technology can be applied to something, a new generation capacitor.
Yeah,
Yeah.
definitely, yes. Capacitors, even regular capacitor, we use it all the time. Yeah, thank you.
Thank you very much.
Question and comment from young generation is strongly encouraged.
Yeah.
Oh,
Hello, thanks. Hello, thanks for the presentation. It's very inspirational. And I'm a PhD student at New York University. So, and also I have 3 startup companies running now. And I'm doing something similar to this by using this food waste into electricity. And I was wondering if you have any study based on this metagenical bacteria, thermophilic bacteria that you can produce electricity out of it.
For bacterial, right? There's a number of years ago, we used some biofuel cell, use bacterial for that. You can integrate with this one. So hybrid energy. If you have a bacterial, you can use bacterial to convert electricity. You have motions, use motion. But integrate 2 into 1 unit. So use whatever is available, whenever it's available. Like solar, you know, like solar. We have light, we use it. We can build a solar cell. On the top of solar cell, we build our TENG. It's transparent. And then you harvest both. You harvest my body motion energy, also harvest light energy, utilize that. So called hybrid energy. And we published the first paper 2009 or 10, use the hybrid energy, but now they get a lot more broad.
Thank you.
Thank you for your wonderful talk. My name is Pang Hong from National Institute for Material Science. And as we know, the nanomaterials are not easy to maintain its properties, so I wonder what's the lifetime of these nanogenerators?
Okay. Depends what kind of nanomaterials. For us, we can use some nanomaterial. We don't have to use nanomaterials. A lot of we do surface treatment. So say how long we can run. Let me tell you the shoes we built. We do the test for 3 years, lifetime. 10,000 steps a day for 3-year warranty on the walk. And if you have the ocean, we now have even better way for extended lifetime. So I think we can, from what we calculate right now, I think we'll be able to run it for at least 5, 6 years right now, but just beginning. This is the beginning. If you give another few years, we can extend to another 10, 20 years for lifetime, because we try to avoid. You know how? Because you don't have to do this all the time. Because once the charge gets on, it remains there for hours. So you can freely work without contact. Use this one for a few hours. You still continue to generate electricity, but no friction. You can use that to extend lifetime dramatically.
Thank you very much.
Yeah. There are a lot of materials opportunity, as I show in the PPT. That's opened the door for. So I didn't mention specific material used for this one. We can use any materials you may have for this. Yeah.
For example, except for the zinc oxide, so what other materials?
Oh, I think you didn't catch my point. This is not all done by zinc oxide. This is done for PTFE, PFE, all these polymers. Zinc oxide is one of them. We can use 100,000 different materials. It's broad, general.
Yeah, okay, thank you very much.
Okay, I'm afraid it is time to close. So thank you again to Dr. Wang for his doing talk. So I think it could be very useful for this SDGs. Thank you very much.
Thank you.